Hey guys, Mr. Adamson here. In today's lesson, we're going to talk about 5 common types of chemical reactions. So this is building off of us naming reactions and building formulas, and we're going to actually be able to identify what type of formula we have. So the 5 common types of chemical reactions are formation, decomposition, hydrocarbon combustion, single replacement, and double replacement. And I'll go into more detail and provide examples on the next few slides. Now, formation reaction. So this is also known as a synthesis reaction, and this is where 2 elements combine to form a compound. So you have an element plus an element, and then you get a compound. So the elements are in the reactants, the compounds in the products. So example of this would be building sulfur dioxide or the making of ammonium. And just to provide a couple examples here, we'll just we can look at, for a formation reaction, we can have phosphorus, which we know by itself is a polyatomic element, plus oxygen, which is a diatomic element, and this gives us P2O3. Now, we also have to balance this, and so we have 4 P's here, 2 P's here, so we're going to put a big 2 in front of here. Now that gives us the balance of phosphorus, and we have to balance the oxygens. We have 2 times 3, and that will give us 6, so then we need a 2 here also. And that gives us a balanced equation. But the overall idea, you can see that you have phosphorus here plus oxygen gives you a compound. So element plus element gives you a compound. Now, the next one after that is a decomposition, which is the opposite of a formation reaction. And this is when the products can be broken down to yield the reactants again. So where the compound now is in the reactants position, and this will give us in the products 2 elements. So you can see there AB gives you A plus B. And you also have practice problems in table A3.5 of your textbook. The next type that we have is hydrocarbon combustion. And hydrocarbons are substances that contain hydrogen and carbon. So, I mean, there's a pile out there. Easily example, you have methane, you have glucose, a lot of those different things. So the general formula for a hydrocarbon is CXHY. And the X and the Y determine how many atoms are in the molecule. So example, butane has 4 carbon atoms and 10 hydrogen atoms. So its formula would be, and from what we previously just said, you would have C4H10. Now, any reaction with oxygen for hydrocarbon combustion, so any reaction with oxygen that is fast and exothermic is a combustion reaction, so exothermic releasing energy. Now, if plenty of oxygen is available to react in hydrocarbon combustions, then there will only always be 2 products, carbon dioxide and water, or water vapor. And you can see there because we have the gas. Now, this is the big thing with hydrocarbon combustion. If you look here, let's get the, we can see that we have our CXHY, so that X and that Y being any number for depending on the hydrocarbon that you have, plus oxygen. So as we see up in this bullet right here, any reaction with oxygen is exothermic and is a combustion reaction, gives us our 2 products, and our 2 products again being carbon dioxide and water vapor. And so that's a big thing with a hydrocarbon combustion example. You always look at what your products are, and if you have carbon dioxide and water vapor, you know you're dealing with a hydrocarbon combustion. And so now single replacement reactions, this is when a reactive element reacts with an ionic compound. So after the reaction, the elements ends up in a compound, and one of the elements in the reactant compound ends up by itself as an element. So the reactions often take place in solution. And so if we look here just with the ABC example, you can see you have A, so the element there, plus BC, which would be the ionic compound, gives you B plus AC, where that A and B are both metals, and they switch place from reactants to the products. And so just to provide a quick example of writing one of those out to see what it actually looks like, we'll look right here. We can go to another new example. So if we have lead, which is a monatomic element, so it's all good by itself there, plus iron sulfate, what would that give us being a single replacement reaction? We know that lead is a metal, iron is a metal, this is a polyatomic ion. So lead and iron are going to switch places. So therefore that would give us Fe plus PbSO4. Now these charges are all able to be taken down to their lowest common denominator, so we don't have any cross-dropping going along in this one here or this one here. However, when we look at balancing it, I have one lead, one iron, one SO4, one SO4. But again, this is a balanced single replacement reaction where we have our two metals, metal 1, and metal 2 in the reactant side, switching places in the product side. So a single replacement. So we have single things just replacing each other. So, and just some examples here, metal atoms trade places with metal ions in a compound. Magnesium metal reacts with the compound silver nitrate as follows. So magnesium plus silver nitrate would give you silver plus magnesium nitrate. So just like the example I gave you before, we have the metal switching places. Now any element on its own is present as atoms, and any metal element in a compound is present as an ion, and that's something key to know, that when you're by yourself in a reaction with a metal, so monatomic, it is an atom. You're not showing a charge or anything like that. However, when you're putting something in a compound, you have to take in consideration of the charges when you have to cross-drop those charges and build that compound. Now another type of single replacement reaction, non-metals though can trade places. So we talked previously about the first example there, how the metals could trade places. Now you can also have the non-metals trade places. So if we look here, we have D plus B and C would give us C plus, and that should be, that's an error there. It should be B, D. So example, chlorine and silver bromide. And if we were to write that out, we know that chlorine, Cl2, so sorry about that, just had a little interruption. However, back to our example, we have chlorine and silver bromide talking about a single replacement reaction here where the nonmetals are trading places. So we have chlorine, which we know is a diatomic element, so it'd be Cl2 plus silver bromide. Silver is Ag, bromide is Br. Therefore, we are going to have our chlorine and our bromide, which are the nonmetal switch places. So we're going to have Br, and again, bromide being a diatomic element, so it Br2 plus silver chloride, AgCl. Now we have to balance this equation. We have two Cl's here, one Cl here, so I put a big 2 in front. Now with my Ags, I have two Ags here, and I only have one here, so I put a big 2 in front. And I look, I have two Brs now, and two Brs, and there we have a balanced equation. But the big focus being that this is another single replacement reaction example, but my two nonmetals are switching places from the reactant side to the product side. And the last type of reaction that we'd have would be the double replacement reactions. And this commonly occurs between two ionic compounds. Ionic compounds are always solid at room temperature, so these reactions happen in. So who could tell me what these reactions would happen in? So where, if they're solids, where are they going to happen? And the answer to this would be when they're soluble in water and aqueous solutions. So then the ions have a chance to mix. And this type of reaction results in formation of at least one precipitate. And so you can see here in the bottom with the alphabet letters, we have AB, so ionic compound AB plus ionic compound CD, where we have A and C switching places. Now, the ions in the first compound join with the ions from the second compound, and the two new ionic compounds are formed. Now, facts to keep in mind. A and C are both positive ions. They will never pair up because they repel one another. A and C will always appear first in formulas because they are positive ions and are written first. And B and D are negative ions, so they'll never combine with they will combine with the positive ions. They are always written in the second formulas because they are the nonmetals. Therefore, their endings also change to "ide" when you're writing them out. And just a couple note here, consult table A2.13 on page 57, or table C in the student reference 12 to determine the states of products in the replacement reactions. Now, this is just kind of a general table that shows you kind of everything. A little quick reference guide. We can see that formation, so you have two things becoming one, decomp, one compound becoming two elements, hydrocarbon combustion, you have a hydrocarbon in the reactants plus oxygen giving you always carbon dioxide and water. Single replacement where you have either the metal atom changing place with the metal ion or the nonmetal switching places, and a double replacement where you have two ionic compounds and the metals are switching places to join up with the other nonmetals. Now, if we just go to show you an example of a double replacement reaction here, we could look that we have sodium phosphate and PO4 plus potassium oxide gives us sodium hydroxide plus potassium phosphate, where we have metal 1 and metal 2. And now, if we look from our reactant side here to our product side over here, we can see that the previous metal of sodium that was with phosphate is now with hydroxide, and the metal here of potassium that was with hydroxide is now with phosphate. So we have two things switching places, which is a little more complex than the single replacement. And one more thing, just to balance this all, we can see we have 3 sodiums here, 1 sodium here. So I need a big 3. Then I can see that I have, and I can keep the OHs together and count them because I have them both on each side. I have 3 hydroxides here and only 1 over here, so I need 3. That gives me 3 potassiums, and I have 3 potassiums here. 1 phosphate, 1 phosphate, therefore it's a balanced equation. And there is just some examples of now the 5 common types of chemical formulas and chemical reactions that you can identify them and know them. When we're doing our projects, you'll be able to do this now in C and with balancing. So I hope you were able to learn a little bit today, and that's it for now.